Now I've got PJ Evans from the National Museum of Computing. He's going to be talking about reading Hitler's mind, Bletchley Park, and the first computer. Please welcome PJ Evans.
I got a woo! Hello! Hello, lovely EMF people. Thank you for coming along. We've got a double bill, Bletchley Park double bill this afternoon, because you've got me talking about the first computer, which was invented at Bletchley Park, and also following that, you've got the wonderful Simon Singh with an operator's guide to Enigma. So we're really going to geek out on cryptography this afternoon. Before we get into it, a little bit about myself. 100 years ago, I used to write for this magazine about this device, and I've been getting a lot of love for the ZX Spectrum. See, people applauding already, especially some great talks yesterday with Ben Heck and all the rest of it, so that's cool. But these days, I am a tour guide and volunteer at this place, the National Museum of Computing, which is based at Bletchley Park. Now that, if you don't already know, is only about 2.5 miles away from here. So a lot of this is going to be me suggesting you go and pay a visit. Because the people of Bletchley Park were very much like you people. These were makers back in the 1940s. These were people who were put in an incredibly dangerous situation and had to think on their feet. And never was it ever more true that necessity was the mother of invention. They came up against a problem so difficult, the only practical way to defeat it was with a computer. The slight problem was the computer didn't exist yet. So what did they do? We do the sort of thing that you guys do. They invented it. So it's a great story, and that's what I'd like to show you this afternoon. Now, if you come to the National Museum, you can come and see this computer. It's called Colossus. It is the world's first digital programmable computer. This is a rebuild of it, fully functional. But the story of how it came to be, well, we have to go back to 1941 to start there. And we start at Bletchley Park. Now, is there anyone here who's not come across Bletchley Park before? Do I need to say anything about what Bletchley Park is and what happened there? Good. Right. That's about 2 minutes off my talk time, which is going to make these guys very happy. So Bletchley Park, home of the code breakers during the war, most famously associated with the breaking of this device by people like Alan Turing and Gordon Welshman. Now, the Enigma machine was in great use by the German military, in fact, the entire German infrastructure, during the Second World War. Its advantage was that it is a very simple mechanical machine that encrypts very strongly. It's very small and portable. For the first time, they could have secure radio communications right down to the front line because of this small little device. But it does have its disadvantages. You need 6 people to send an Enigma message. One to use the machine itself, to encrypt the message, type the message in, watch the lights as they light up and what letter they correspond to. Then you have someone who needs to write all that down, and then you need someone who needs to transmit it by Morse code. At the other end, 3 people have got to reverse that process, ending with typing the enciphered message into the Enigma machine and seeing the plain text come back up. That's 6 people who can introduce human error into the problem. And they did a lot. Also, it's not very suitable for very long messages. It's about, you don't want to send anything over about 17,500 characters. And also very slow. It's restricted by Morse code, which is a human-operated thing. Now, Hitler and his top generals needed something faster and more reliable for their top-level communications. And they were interested in this technology, teleprinters. Now, a teleprinter was a bit like the first text messaging system. Typewriter-like device, you could sit there, type away happily, and another teleprinter hundreds of miles away, tuned into it on shortwave radio, will receive the signal it's broadcasting and output what you type on their paper. And they can chat back to you as well. Another advantage was that you could prepare punched tape, and you could have pages and pages and pages of documentation that you need to send, encoded in this punched tape, and feed it into the machine. As all the broadcast and receiving was automated, it could go much faster, about 7 characters a second. In fact, it's such a robust technology, it's still in use today in maritime applications. And if you come to the National Museum of Computer, you can hear live transmissions from Hamburg. The punched tape, because we're going to get into this a little bit, that's what it looked like. It's actually very easy to learn to read it. If I show you an overlay, it's a 5-bit code, and on that orientation, each horizontal line represents 1 letter of the alphabet. and it is a combination of 5 marks or spaces, the holes and the gaps. So there we've got J and U as an example, just like the dots and dashes in Morse code, but always in 5. So we refer to it as a 5-bit code. Now, the problem was that this was very fast, very reliable, but not encrypted. So anyone listening in could just take the signal, plug it into their own teleprinter, because this system was an international standard, and listen to what was being said. That was no good, so they built an attachment for it. The most fiendish encryption system the German military ever had. And this is a picture of one. There's only 2 left in the world that we know about. Please check your lofts. If you've got one, let me know, okay? I'll give you a 10 or 20 quid tops for it. And this one here is actually the only one that works still. The other one's too badly corroded. Take note of the 12 rotors across here, or wheels as they're sometimes referred to. That comes into it later on. What this device would do was take the paper tape coming out of the teleprinter machine, it would be fed through this, automatically encrypted, and then fed into a radio broadcast system. At the other end, that process would be reversed. And just to make sure it was absolutely secure, it's capable of 15 billion different key settings. So, there's our new workflow. Operator uses the teleprinter, goes through the Lorenz machine, the Lorenz SZ42, and into the radio equipment. It's then broadcast, and the process is reversed. The upshot is, you can stand there, type away quite happily, and the operator at the other end doesn't need to do anything else, just sees the plain text German coming out, but in between, if you know the old Alice, Bob and Eve paradigm, so Eve in the middle only gets the encrypted message. Fast, reliable. Huge though. If you had a mobile unit, it took 3 trucks to move it around. So it was only used for high-level networks. So what they did is they decided to build a communications network for the top military. Now, they don't exactly write to Bletchley Park and say, oh, and by the way, we've set up a new network, you might want to take a look at it, something new. Here's how it all works. Of course, Bletchley Park had to discover it. And they did. What happened was that the Metropolitan Police started picking up a new signal, and it sounded like this. Well, it would have if my audio was working. Awesome. Now, any of you who've listened to Morse code know that's not Morse code. It's going way too fast for Morse code. It was actually nicknamed non-Morse by Bletchley Park. We now know it today as International Teleprinter Code. And what they realized is that these codes were being sent out from Berlin using directional antennas, and a big major network was being built up. It got nicknamed FISH at Bletchley Park, because he loved the little names, and each spoke of the network was named after a different fish. So we've got codfish, what's the one? Turbot, dace, and then they forgot what fish were, so they called it octopus, squid, and so on and so forth, as this network was built up. First job to do was to start monitoring these new signals. So they set up a dedicated listening post known as a wireless intelligence station at Ivy Farm in Knockholt in Kent. It's still there, that's actually a very recent picture of it. About 300 staff worked there, mostly Wrens, the Women's Royal Naval Service, and their job was to intercept these new signals and transcribe them. Our teleprinters, for reasons I haven't got time to go into now, couldn't understand the signals, so they actually had to painstakingly record them using a device called an undulator. This is a piece of undulator slip, and it's a visual representation of that radio signal. So the high beeps are the peaks, and the low beeps are the troughs. So what's not obvious here, that these are all in groups of 5, and it's a truth table, it's true or false. So we've got, for instance, true, 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 false. That's a 5-bit code, mark, 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 space. So the Wrens would have to read that individually and then transcribe it back into the original punch tape form so that it could be analysed. Painstaking job. A few months ago, I was giving a talk at the National Museum of Computing, and I was walking along with a piece of this actual slip, and went past a nice little old lady, and she started reading it out to me. She said, oh yes, that's an A, that's a Z. 70 years old on, and she could still do it. She worked at Knockholt. When Knockholt had the signals, they sent them up to this building, F Block in Bletchley Park. It's sadly no longer there because BT thought it would make a much better car park than a very historical building, so that's what happened to it in the 1980s. But the building just through it there that you can see, at the background through the arch, that is now the National Museum of Computing. That's H block. And you will actually go up that very same road. F block was set up to analyze these signals. But what they didn't realize then is it was about to become the world's first computer data center. But we'll get to that in a bit. So, messages are being captured. They're being set up to F block for analysis. And they are getting nowhere. With Enigma, the machine was commercially available before the war broke out, and one of the codebreakers, Dilly Knox, owned one. The military version, which was much stronger to use, had been captured by the Poles. They'd built replicas of it, analysed all the wiring, and given all that information to Bletchley Park. So a lot was known about Enigma, and that gave them a head start in getting into it. This new thing, though, this new cipher, they knew nothing about it. We didn't even know what the machine looked like or what it was called, never mind how it worked. And it stayed like that all through 1941. At the end of 1941, something remarkable happened. A new branch of the network is being set up between Athens and Vienna. One night, 2 radio operators are testing out this link using the teleprinters, and they're chatting to each other on the keyboards. They're not encrypting, because they're not saying anything particularly important. They're just testing the equipment, but Knockholt is listening in anyway. Suddenly, one of them announces that he's about to test the secret writer. Knockholt gets very interested. He then does something no one's seen before. He says, "Here are your settings," and sends these 12 letters. Now, if you know about Enigma, then you know that you've got to talk about rotors, plug board settings, ring settings, things like that. 12 letters, this was something new. He then sends around a 4,000 character message. He's not prepared it in advance. He types away at his teleprinter. At the end of the transmission, which took quite a while, Vienna radios back and says, "Sorry, old chap, didn't get that. Could you send it again?" I think he was annoyed, because he then went on to make 2 of the greatest mistakes in the history of cryptography. Mistake number 1. He said, "Okay, I'll send it again. Use the same settings again." Now, if he'd sent that exactly the same, if he'd used a punch tape, Bletchley Park would have been none the wiser. But he didn't. He made abbreviations all the way through, about 100 characters shorter the second time round. Now, in cryptography terms, if you get that, it's called the depth of a message. They'd never had a depth before for this new cipher. It was the first time they had the settings and 2 messages from the settings. So they were able to compare them mathematically. And that's exactly what this guy did. Brigadier John Tilton, arguably one of the greatest codebreakers ever to work at Bletchley Park. He was specializing in Japanese ciphers at the time, but was brought over to F block to work on this new one, with this new information. He spent about 6 weeks analyzing the 2 messages, and in a stroke of brilliance, cracked it wide open. He realized they were using something called a Vernam or one-time pad cipher. So I'm going to briefly explain how this worked. The first column here is our message in this 5-bit code form. And what we've got here in our example is the letter M in International Teleprinter alphabet. What this device was doing was generating a second series of patterns, the same length as the message, and pseudo-random. They had to be pseudo-random. And then it would perform a little mathematical trick called XOR on it. Now, just to explain what happens, XOR basically means if they've both got a mark, then put a space. If they're different, put a mark. If they both have a space, put a mark. So, on the M, if you look at the first column, there is a mark. On the N, there is not a mark on the first column. Therefore, that scores true, put a mark. For the rest of them, they're all the same. It's mark, mark, space. That one's mark, mark, space as well. So you say nothing. That is your encryption process. We now have the letter T, and that's the ciphertext that you send. At the other end, an identically set up Lorenz machine generates exactly the same key stream and reverses that process, and you get your letter M back. Now they had this information, 2 things needed to be worked out. Firstly, how does it do that? How does it generate that stream? It can't be truly random, it must be pseudo-random. How does it work? And secondly, how do you work out where it started? If that's a circular stream, you've got to find out the starting point, just like with Enigma. So here's how the break worked when Tiltman had this moment. Here is some ciphertext from the first message. And this is the ciphertext from the second transmission. What Tiltman noted is that a few letters in, here, it changes. So he quite rightly assumed that the first few letters of the message are going to be the same in both. And then he had a stroke of genius. He figured that both these messages are a combination of the key stream and the plain text message, added together using XOR. If he adds both of them together using XOR, the two key streams cancel each other out. And what you're actually left with is a new piece of text which is just a combination of the two plain text messages. The key stream, the encryption bit, has gone. What you need to do now is crib the message. You need to come up with words or phrase that you know is going to be in that message. Thankfully, the Germans were very helpful with this. The German military were very fastidious. They always kept to doing the same thing, following procedure over and over again. Tiltman already knew that the first two words were definitely going to be Spruchnummer, message number. So he thought, well, okay, if I take Spruchnummer and add that using XOR to my... Where's my screen gone? Yay, it's back. If I take that and I add that to my combined two messages, it should remove that and then produce the other message. So if I add that and I've got it right, what should come out is another piece of plain text German. So we did the first few letters and got that. Spruck NR. NR, like we shorten number to NO in the English language. He knew he'd broken it. A few hours of teasing the message out later, he had the first full break. So now we knew how to break this message if they had the settings. But there was still a long way to go. Firstly, they had to work out how the machine itself worked. That fell down to a man called Bill Tutt. Anyone here heard of Bill Tutt? That's really gratifying to see. It's great that his name's getting known because we're campaigning long and hard because what this man did was incredible. He became obsessed with the problem of figuring out how this machine worked, how to reverse engineer it. And he spent 3 months working at Bletchley Park. He used to sleep at his desk a lot. One of his co-workers thought he was actually wasting everyone's time because he just seemed to stand and stare out the window for hours on end. But he was wrong. He was thinking. At the end of that period, he astonished his colleagues with this diagram. It explains, with 100% accuracy, as it turns out, exactly how this mysterious machine worked. They've never even seen a picture of it. All they've had to go on is those radio signals, and now they know exactly how it works. Those 5 bits that make up each letter were passing through 2 sets of 5 rotors. The first set, the K wheels, always make a change to the letter and then all rotate and change the next letter in a different way. The second 5 only turn sometimes, so they might make the same procedure on a multitude of letters. Whether they turn or not is controlled by the 2 motor wheels at the bottom. 12 wheels, and if you remember, there were 12 letters. The historian Jack Copeland described this as the greatest intellectual feat of the Second World War. Us at National Museum of Computing, being completely biased, completely agree. What this allowed Bletchley Park to do was build their own version of this remarkable machine. And they called it Tunny, the old name for tuner. Now, the Tunny machines, this is a very rare photo of the actual real Tunny machines at the time. One of the frustrations of being a presenter and talking about Bletchley Park is there just isn't that much, they weren't exactly running around with cameras. There's very little evidence that this place even existed. So I've got a better photo here, and this is taken from our rebuild of a Tunny machine at Bletchley Park. It's fully operational, and every day, all day, the tour guides, people like myself, will actually demonstrate it operating for you. If it looks a bit like an old telephone exchange, it's because it's an old telephone exchange. And the reason for that was simple. They need an electronic device for speed. And the best people at electronics were the General Post Office, who were currently building out the telephone network. So they took the requirements to them at the research centre at Dollis Hill, and that's what they came back with, because that's what was in the parts bin. These rows here represent those 12 wheels that make up this machine, the Lorenz. And once you knew your settings, you would plug up the machine, and then the teleprinter in the corner, if it all works, you should be able to type on the teleprinter, and what should come out on the page should be plain text German, if you've got the settings. And that was the problem. The Athens and Vienna messages were highly irregular. They did not normally send out the settings at all. What they sent out was a number. No one at Bletchley Park knew what that number represented. And it was, in fact, at the end of the war, they found the operators' code books, which they would open to the page number, and there would be all your settings for your Lorenz machine. Of course, they didn't have that, so they were stuck. John Tiltman had actually worked out a way of breaking Lorenz. You needed three things: a pencil, a big pad of paper, and about 6 to 8 weeks per message, providing you didn't make any mistakes, which of course they did all the time. And so this was a problem. The information obviously was stale. They used different settings on every single message they sent, and there was about 300 a day coming in at that point. 6 to 8 weeks wasn't going to work, but that's how they did it to begin with, because it was the only option they had. The question was asked, could we build machines to speed this up? You see, Tiltman, also with Alan Turing's help, had come up with an algorithm. And if you ran through all the permutations of the starting positions of the first 5 rotors of the machine using this algorithm, you got statistical information out. Correct analysis of this statistical information, which is very hard to say, would result in locating those first 5 wheel settings. Because of the way the second group of 5 worked, only turning sometimes, that actually turned out to be a gigantic Achilles heel for the machine. And you only needed about 2 to 3 hours to actually figure out the remaining 7 settings. But at the first 5, 6 to 8 weeks. They went to a man called Max Newman. He was a bright chap. He taught this guy at university. So he set up the Newmanry. And the Newmanry was responsible for designing machines to help F-Block analyze these messages faster. Their first attempt looked a bit like this. It was nicknamed Heath Robinson by the operators. And it was quite an incredible machine. It basically sped up the counting that had to be done to run through this algorithm for use of relays. The tape was pulled around by sprockets and passed a tape reader, and the relays would clatter away happily, producing this information. It did speed things up. It actually brought the break time down to about 2 to 3 weeks, provided it didn't explode, which it did quite a lot. There were stories in the official reports of some of the workers going in and just seeing clouds of smoke as yet another relay is gone. And also, the sprocket system would wear the tape out quite rapidly as well, so that would snap. So it wasn't a great design, but it did show the way forward. GPO was asked to consult on the project to see if they could make any improvements, and this man took it on. Anyone heard of Tommy Flowers? Hey, good. Tommy Flowers, head of switching at the GPO at Dollis Hill, and he looked at it and said, no. It needs to be a lot bigger, and these slow relays, we need to replace them with something much faster. We need to replace them with valves. Doesn't have to be anything fancy, and that's just a standard Pento valve there. And so he designed a machine that used 1,500 valves. He presented the design to Bletchley Park, who told him to get lost. Why? Because they had radios, and they had about 2 or 3 valves in them, and they were a nightmare. The valves failed all the time. A machine with 1,500 valves is insane. And he said, no, what kills valves is thermal shock. They do not like being switched on and off again. So all we've got to do is leave this machine running 24 hours. And they said, absolutely not. But if you want to build it on your own pocket, go ahead. So we did. At Dollis Hill, still standing today at the research centre, now luxury flats. Isn't everything luxury flats these days? He designed and built his Colossus Mark I, 1,500 valves. The results were incredible, and Bletchley Park got interested. Not only did they approve his Mark II version with 2,500 valves, he also ordered another 9. Only 9 photographs exist of the original Colossi, and this is one of them. But let's have a look at the machine in a little more detail, if this is going to behave. Is it going to behave? Please behave. Yes, there we go. So you'll see some images of there. So what we've got is an improved version of the Heath Robinson. You have a bedstead there. The tape on this is running at 30 miles an hour, reading at 5,000 characters a second. Uses tension to drive the tape around so it doesn't break. And also you see there a light source reading in the message. So the light goes through there, through some lenses that blows it up into 5 photoelectric cells. And you could not just nip down to Tandy, or this shows my age, doesn't it? To Maplin and buy 5 photoelectric cells. They were actually considered military top secret at the time. All that gets read in time and time again into the machine. The valves are actually generating the key stream of the Lorenz machine, applying that algorithm, making decisions based on it, which is why it's a computer, and then creating statistical data. Now, the reason they had to have that at all running around on that bedstead was because they had no memory. Colossus has 0 bytes of RAM. They hadn't got that to that point yet, so it had to be read in time and time again. So that acted as its storage. At the end of the run, the teleprinter at the front here would spit out some statistical information. One number above all the others would stand out to the code breaker, and that would tell them what the first 5 rotor settings were. Because of that flaw I mentioned earlier, the remaining 7 was only a few hours' work away. And in fact, another machine called Dragon speeded that up as well. So let's review timings. By hand, 6 to 8 weeks. With a working, non-fire exploding Heath Robinson run, 2 to 3 weeks. Colossus could finish its run in under 3 hours. With this machine, they started decrypting messages in bulk. And what they found was that this network was being used by Hitler himself, often signing the messages personally, to give information to his generals in the field. Now, Bletchley Park had a direct insight into what this man, who used the term advisedly, was thinking. So a quick timeline of what happened. Just to point out, because I want to give some credit to the code breakers before Colossus here. 1943, Battle of Kursk, the first big Soviet victory of the Second World War, and still to date the largest tank battle ever. Part of the reason for that success is that a few days prior, the code breakers had cracked the entire German battle plan by hand. And they sent that information to the Soviets, never telling them the source though. November 1943, the Mark I goes live at Dollis Hill. And in January 44, it's moved to Bletchley Park. It starts breaking real keys in February. On the 1st of June 1944, Colossus Mark II, the 2,500 valve version, goes live at Bletchley Park. Date might ring a bell with you. On the 5th of June, a piece of information is decrypted so important that Tommy Flowers himself meets Eisenhower, head of the American military at that time, and the Allied forces, to deliver it to him. A secret meeting is held. He hands the information to Eisenhower. Eisenhower doesn't say anything to anyone else in the room about this information, where it came from or what it said. What the information said was, move your generals from Normandy to Calais, signed Adolf Hitler, Führer. Operation Fortitude had been a success. Operation Fortitude was an audacious campaign to fool Adolf Hitler into believing we were going to go into Calais, not Normandy, so we would move his troops away and leave it poorly defended. This included gigantic inflatable tanks. Sounds crazy, but if you imagine, and we're now at 1944, the fields of Kent were covered in hundreds of these inflatable tanks and canvas Spitfires. A fictitious army, the first American army, was invented and Patton put in charge. So, of course, the reconnaissance planes came over and saw them all massing in the perfect location to launch an assault on Calais. When he read this information, Eisenhower just put down the paper, looked at the other people in the room, and said, we go tomorrow. 6th of June, 1944, D-Day. So, I've only got a few minutes left, so quickly, what about the legacy of Colossus? We've seen how it played a vital role in the closing years of World War II, but what happened after that? Well, all 10 colossi were destroyed, taken apart for spare parts, and also to help protect their secrecy. That's what GCHQ tell me to say, it's not what happened. Actually, what happened was this. The Russians came into the east of Germany at the end of war, and they found Enigma machines. They had nothing of this level of sophistication, and of course, we'd not said a word to them about being able to read Lorenz messages. They did exactly what Churchill wanted them to do. They didn't improve their own existing cipher technologies, they adopted Lorenz. 2 colossi were taken here to GCHQ Eastcote, which was the next stage of evolution of Bletchley Park, and then later on down to Cheltenham, which of course are still there to this day. And those 2 colossi broke Russian Lorenz messages right through the Cold War to about 1965. What about the other people involved in the project? Well, Tommy Flowers went back to a fairly ordinary life, working at the post office. Of course, never spoke a word to anyone about what he was working on. But suddenly, a lot of the universities around here got very good at building computers. In the late 1940s, we had the Manchester Baby, and a remarkable machine. Who was head of that project? Oh yeah, our friend Max Newman. Of course, they knew nothing about what he'd been up to. And his colleague, Alan Turing. Well, he started building computers as well. He built the Pilot Ace with his team. He never got to the end of the project, but you can go and see that machine in the Science Museum in London. And in Cambridge, the EDSAC got built. EDSAC's currently being rebuilt at the National Museum of Computing. You know, see, I keep getting the hints in. Yeah, it's really good. And that will be going live. It's actually been tested for the first time this weekend, but it'll be going live in 2015. EDSAC project was funded by Leon's. Now, they were the Starbucks of their day. There was Leon's tea shop on every corner in the 1940s, 1950s. And they had a massive problem with inventory and delivery. And they had enough foresight to think, well, maybe these newfangled computers can help. So they actually helped fund the EDSAC project, and EDSAC became the prototype for the Leo Mark I, the world's first business computer. And from the Leo, Leon thought, oh, we're onto something here, and they set up a business, Leo Office Systems, the world's first commercial computer company. Suddenly, computers are broken out for military and academic purposes, and before you knew it, they're everywhere. But we can all trace it back to Tommy Flowers and his incredible machine. So I've got a few seconds left, so we're going to absolutely, totally pitch this as hard as we can. Some of the amazing things you can see. You can see the Witch, the world's oldest original computer by about a decade that still operates. It's the original one, still working away, designed in 1949. Incredible. And this will blow your mind. If any of you are techies out there, I think I'm a pretty safe crowd for that. It doesn't work in binary, it works in decimal. Think about that. I don't get it either, but you can see lots of old computers and stuff. And better still, we're a hands-on place, so we let you go and play on them. We want people to be hands-on, get on those computers. Even more, you can become a volunteer. And you can help restore them. We desperately need people to come and help. It's like a playground of tech, honestly. And you don't need to live nearby. You can donate an hour a month or 8 hours a day. It's completely up to you. If you're interested, please come and see me after the talk. And it's really, really close, if I haven't pointed that out already. In fact, pick your favorite unit. But of course, most importantly for you guys, we do have perfectly acceptable coffee. Wrong way. There we go. All right, I better be quiet now. Do hang around for Simon Singh's presentation on Enigma. Have we got any time for any questions? Or are we looking a bit tight? Do come and find me if you do have any questions. Are we saying no? We've got to get going? We're saying no. Boo. Okay. But I made a question slide. Okay. All right, never mind. I'm out of time. But thank you very much for coming and hearing the talk, and please to come and support the National Museum of Computing. Thank you. Thank you.